Good morning. All right, let's get all the panic out or make the panic worse. Either way, right? This is your time. What are we doing? What? Note taking? Is that what you said? Oh, helping. Yes, I will help you, but I need to know how to help you. You need to ask questions. Yeah. Yeah, centripetal acceleration. What about it? What the heck is that? So we did a vertical loop. That was centripetal acceleration. We did, we did the banked turns. That was centripetal acceleration. We did, what was it, car on a turn kind of thing that wasn't banked. We did that. Anything that moves in a circle has centripetal acceleration. Acceleration points towards the center, which is calculated as v squared over r, right? But just that kind of that concept and idea. Now, I'm saying centripetal acceleration. That could mean it's involved in the problem or it is the problem. So like in the vertical loop, it's involved in the problem. The acceleration points towards the center, right? But we still had to do a free body diagram, all that kind of stuff, right? So it could be that, or it could just be calculate the centripetal acceleration of something that's moving, right, going around in a circle, right? So there's a lot of variation in difficulty there, right? But that's kind of covers sort of what we did together and what you were doing on your homework, right? I hope that answers your question. I brought up difficulty. Let's talk about which of these are probably like, maybe not even the most difficult, but the ones that will take the most amount of time. Which of these take the most amount of time? Anything from chapter 4, right? Doing an inclined plane problem with all of the free body diagram and the finding of components and the developing of equations and solving for the unknown. That's time, isn't it? Static equilibrium, pretty much the same thing. It's just there's no acceleration, right? Acceleration equals 0, so boom. But it still takes time because you need to figure out components, all that kind of stuff, right? Orbital mechanics, power, even centripetal acceleration, I'm not expecting those to take too much time. Okay? I do try to find a balance. Like some problems I know, like inclined plane and static equilibrium, are probably going to take 15 minutes to do. So is there a way for me to write another problem that only takes 5? Right? The average is 10 minutes per problem. But if you can answer the conceptual one in 5 minutes, if you can do a quick power calculation in 5 minutes, right? You're saving times on other things. So again, what are you going to do when you first open the exam? Skim through it, identify the ones that because the topics, these exact topics will be on there, right? So find the one that says static equilibrium, save it for last. Find the one that says inclined plane, save it for last, right? Try to tackle the others. Energy could take a little while, but it's usually faster than Newton's laws, right? So strategize out that, right, at the very beginning, knock out the ones you think you can do, and then come back to the ones. I made a little tiny mistake on the green ones. You don't need to remember this. It's not going to be that big a deal. I think I forgot. So I think problems 5, 6, and 7 are all on their own page. Usually it's 2 questions per page, and then the 7th one is on its own page. I made a formatting error, and I put in a page break where it didn't belong. And so just remember, every test has 7 questions on it, right? Do 7 questions, even though the green one's slightly formatted differently. I could have it reprinted, but I didn't want to waste all those trees. So yeah, just in terms of general thing. Okay, so inclined plane, we did that, right? It will not be connected objects. So it won't be as hard as what we did in lab, but it'll be related to what we did in lecture and in your homework, okay? Newton's laws conceptual, basically anything goes from the first to the third law. There's really no concept for the second law, right? Second law is just all that math, okay? But first and third law, sing a song type question. Static equilibrium, which I didn't cover static equilibrium in lecture. It is in your homework and is in the book. It's Newton's second law where the acceleration is equal to 0. So it tends to like mathematically be easier. Centrifugal acceleration, orbital mechanics. That's a catch-all term for gravity. So like Kepler's third law typically involved here. Anything moving in a circle under gravity, calculating the period of an orbit, the mass of a planet. We did that in class. That kind of stuff, right? That's what I mean by orbital mechanics. You're not going to be calculating spacecraft, transfer orbit trajectories or anything like that. Conservation of energy we did a lot of, and power, right? Like energy divided by time or force divided times velocity, right? Power and centripetal acceleration are meant to be somewhat quick, and the conceptual question. I'd say if there's any 5-minute problems on the exam, it's those 3. Everything else will be kind of involved. This is a hard test. It's hard not because I sat there and went, how am I going to make this hard? But rather it's hard because like there's so many pieces. It's process instead of just picking an equation. You got to develop your equations, right? A lot of that going on. Give me every reason to give you partial credit, right? Just get it all out on the page. Even if it's wrong, like if it's wrong and you think it's wrong, just a single line through it, flip it over, give me a note, more work on the back, whatever. Show me everything. The 0, 1, 2, sometimes I'll take off, I'll give partial credit, I'll give you a point back for like getting an inclined plane set up correctly. And then maybe you make some math errors along the way that are more than just a calculator error, that are like algebra errors. I'll give you a point for getting it set up correctly. So, right, just show me everything you can. Give me a reason to give you points. All right, other questions, things you have to know about, things you want to go over, things you're not sure about. I've either made you very, very afraid, nobody wants to ask questions, or you're so lost you don't know where to start. Yeah? Some of you are like, So where do you want to start? Which of these topics is giving you the most fear? Chapter 5. Centripetal acceleration, orbital mechanics. Pick one. Orbital mechanics. What do we know about orbital mechanics? This is from memory, so I do not guarantee anything that I've... did you guys... Somebody caught the error I made in the conservation of energy equation, which I corrected. Couldn't correct it in the YouTube, but I corrected it in the PDF. So I make mistakes too. Let's see. Can I remember Kepler's third law from scratch? No. That is wrong. That, I believe, is correct. This is why I have a whole binder full of cheat sheets. One for every chapter. Let's see. Nope. Got to find the right chapter. That is correct, but it's not the way your book wrote it. Your book wrote this. But those are the same thing. So here's your books, okay? We'll get rid of that one. So Kepler's third law, what's the big T? it's a period. And there's another way that we can find a period. Well, we can use the fact that all orbits are circles and find the orbital velocity. Okay, so that's one way to find a period if we know an orbital velocity, or if we know a period, we can find an orbital velocity. Key things about like this r, that distance. What are we measuring between? Center to center, right? So be careful, right? Sometimes they'll say like an object like a moon or something has a certain altitude. Altitude is always measured from the surface, right? So watch out for that. That's an altitude, whereas this distance right here would be the orbital radius, center of mass to center of mass. What mass goes in here? Yeah, the big thing, right? Okay, the mass of the thing being orbited. In the problems we give you, there is one object that is dominant, right? That is causing the majority of the gravitational field. And so you put the mass. So just by way of making sure you understand what this is, if it's Phobos, one of the moons of Mars, what mass are you putting in there? Mars's mass. If it's Venus, what mass are you putting in there? Mass of the sun. If it's an asteroid in the asteroid belt, what are you putting in there? The sun. Okay? Because the asteroids in the asteroid belt are in orbit around the sun. If it's the Hubble Space Telescope, what do you put in there? Earth. And if you're not sure what this thing is orbiting, what do? Ask. The question is not about you being able to like memorize all the different parts of the solar system or something, right? It's to find out, can you do orbital mechanics? So if you're not sure what's being orbited, Mr. Bale, I don't understand the question, right? And then we'll sort it out. The other way to get, the other toolbox equation I have is the orbital velocity is big G mass over little r. It's another way to find it. So there's lots of little ways to find it. Okay, but that's orbital mechanics. Newton's universal law of gravitation is involved, but it's never calculated in orbital mechanics. So I'm not asking you about Newton's universal law of gravitation. If I was, I'd put that as the topic, Newton's law of gravity. So I think, beyond doing example problems of that, that's the whole enchilada when it comes to orbital mechanics. Now, centripetal acceleration. Oh, that was a bad acceleration. Excel, there we go. Okay, so the one and only equation I can remember from this is v squared over r. The v equals 2 pi r over t also applies for anything going around in a circle. Where this gets intersected with Newton's laws is in Newton's second law, where if this object is going around in a circle, it has centripetal acceleration, we can identify the force that's causing the object to go around in a circle, and we substitute in v squared over r for the acceleration. That's really kind of the only change, right? So for a tennis ball on a string, what's the centripetal force? The tension. For a car going around a curve, what's the centripetal force? The friction between the tires and the road. And then if it's a banked turn, then it's the normal force. Find the either the force that points towards the center or the component of the force that points towards the center. And you've got it. I don't have in my I do. Your book said that a banked turn follows this equation. So book equation, book equation, book equation. I choose to write it like this. So that equation will give you the safe speed at which to negotiate a turn, right? With no friction in it. So it doesn't apply to all banked turns, but for banked turns, frictionless banked turns, it works. So you probably want to go through and like label, right? Like banked turn, because does the banked turn equation help if it's a vertical loop-to-loop? No, right? So you got to worry about that. A vertical loop-to-loop on a roller coaster is the same as a vertical loop on in an airplane. Okay. Yeah. I think the only other did you do a problem where like a car or something's going over a circular hill? That was not you guys? That's physics 4A. Never mind. What's that? You're 2A. Yeah, I thought you were 4A also. The problem is that the internal reflex is 4A, because that was what I was trained in and all that kind of stuff. And so I basically have to edit on the fly while I lecture in 2A. And be very careful about what I need to make sure I don't say a lot of stuff. Because the 4A stuff requires calculus. Basically, it's got calculus in it. I have to ignore it. So, I think that covers the range of chapter 5. I want to go back and say something about chapter 4. Just so you guys know how the sausage is made. I understand that these are long problems, right? Again, I sort of hinted at the fact that I try to make other problems shorter or something like that. I can also artificially shorten these problems. Part of the difficulty that makes the problems long isn't just the setup, it's the solving of equations once you've got the equation set up, right? Having to solve, eliminate unknowns and substitute things in. I can just give you one of the unknowns. Like I can tell you, if it was connected objects, I could tell you the tension in the wire, right? And that would actually make the math really fast. You still have to set up the problem. You still have to get the equation right. But then you only have one equation and one unknown to solve for, right? So those are things that I do as I'm looking for ways to get a problem to fit in your 10 minutes. Do you know how I gauge this? I do the problem, and if it takes me longer than 2 minutes to do the problem, it's too much. I figure if I can do a problem in 2 minutes, you can do it in 10. Some of you were like, no, Mr. Balogh, multiply by 10, not 5, right? I get it, right? So I try to do the whole test in 10 minutes. I try to do 7 problems in 10 minutes. Figure if I can do 7 problems in 10 minutes, maybe you can do 7 in 70. If I wasn't on your side, I would just throw as many problems at you as I think, I could and let you suffer through 70 minutes. I had lots of classes like that. You'd walk out, totally failed the exam. Get the exam back. I think the lowest score I ever got in an exam was a 35, 34. That turned out to be a high B. Yeah. We all walked out going, dude, we're becoming English majors. This sucks. And then we walked out with B's. We're like, no idea what happened. None whatsoever. I try not to do that to you. All right. Other questions? Did I give you more to worry about in chapter 5? Should we try an inclined plane problem? Yeah. Should we just make something up and see what happens? Just we got to get the rust off, don't we? I was watching the Olympics and I was watching bobsled, and my wife thinks that the term monobob is hilarious, and I have to agree. At the end of the bobsled track in Italy, the racers come past the finish line, and then they go up a slope. And my wife asked, why did they make them go up at the end? What's the answer? It's to slow them down, right? Okay, because the sled has brakes, but they also are just trying to get them to slow down by having them come up a little bit, right? So we're going to do the part that they've passed the finish line and they're going up the slope, okay? And we're going to calculate the acceleration that a bobsledder, right, or a skeleton or a luge, whatever, right, what they might have as they go on the uphill portion after the finish line, okay? So that's what we're going to do. So what does a bobsled look like? A box. Okay. Yeah, hot dog, whatever. Okay. Okay, so what question are we asking? Well, that's what we want to know, but what question are we asking to be able to draw a free body diagram? No. What forces, what objects are pushing or pulling, right? Okay. So what's that force? Where does it come from? The surface, the ice surface of the ramp of the hill. Okay. What else is pushing or pulling? The earth. What else?
Are we thinking friction?
Yeah, there is some friction. It's small. It is ice, right? But there is some friction. So, in order to figure out the direction of friction, we have to know what direction the bobsled is moving. Which way is the bobsled moving? It's going up. So which way is the friction? It's down.
Is it friction is always opposite of acceleration?
No.
Which one's
Friction is kinetic friction is opposite velocity. Yeah. Acceleration is independent of friction. Okay, so the friction comes from the surface also, right? So the surface causes two forces, friction and normal force. If you're told the surface is frictionless, what do? Just don't put friction in, right? Okay. So are there any other objects? No. Let's just assume they're not braking for whatever reason. Right? If there were brakes here, we'd have a braking force that also would point down the slope, but we're not doing that. They're just sliding up, okay? So, what's next? Great, I got forces. What's next? Coordinate frame, coordinate system, be able to talk about what's positive and negative. So, to do that, what do we do? We really need to kind of decide what the direction of acceleration is here, right? So you get two choices, up or down the slope. Why am I saying only up or down the slope? Because acceleration is not happening outside of the slope, right? Acceleration is not going this way, right? Because if it were going that way, the bobsled is now flying off the hill, right? So that's not happening, right? The bobsled's acceleration is going to be along this line. The only question is it up or down the slope? It's down the slope. Why is it down the slope? It's slowing down, right? It's moving up, but it's slowing down, right? So we'll say acceleration's down the slope. If we're wrong, then we'll just end up with a negative sign in our answer. That's okay. It's not okay? All right. So which way is positive x then? Good. Positive y. We'll just make a way. As long as it's perpendicular. Okay? Let's see. We got a coordinate system. We've got forces. Should we just find components right now before we go on to do anything else? We know that we got to find components, right? And do we have to find components of normal force? No, because it lines up on the y-axis, doesn't it? What about the friction? No, it's aligned along the x-axis. So what's the one we have to find? mg. Okay. So what is this component right here? It's always stayed the same. Which one? It's cosine. Okay, because it's always been cosine, but also because we know that that angle theta is the same as the angle of the hill, and since the component is touching the angle, it has to be cosine. So where's the other component? Pointing down the slope. mg points in and down. So we have our in to the hill. Now we need our down the hill. So I'm going to draw another force right here. And what's that force? mg sine theta. Okay. So now we got our free body diagram done. What do we do next? We have our template, right? It's x and y. What do they both start with? ma equals, technically x direction and y direction accelerations. And we can say something right away about the y direction acceleration in this problem. It's equal to 0 because we made it 0. We made sure that the acceleration was only in the x direction. All right? What goes after the ma x equals? Kinetic friction. Just trying to make sure you understand it's kinetic and not static. Are there any other forces along this line? No, just these two, right? So now we go back and do the signs. Both positive? Why are they both positive? They're both pointing down the hill. We said down the hill is positive, right? What you want to do is say, well, one of them has to be positive, one of them has to be negative, because that's what we did in class. The signs change depending on the situation of the problem. Follow the process, not the results.
I'm a little confused on how we did identify that. Well, so we identified acceleration as pointing in that direction. We determined that because the acceleration is decreasing when it's going up, so it's increasing over.
We basically just guessed. We said as this thing goes up the hill, it's going to slow down. So if it's moving up the slope, in order for it to slow down, if the velocity is up the hill, to slow down, what direction does the acceleration have to be? It's got to be opposite, which is down the hill.
Because the acceleration is pointing down, we understand that x has to be positive.
Yeah, we make sure that our positive direction is in the same direction as our acceleration. We don't lock ourselves into making up always be positive. Because if we did that, if we said this was positive x and this was positive y, then we'd have to remember to put signs on our acceleration. That minus sign right there is the one that's always forgotten if it's taught that way. Like 90% error rate right there. So over time, physics education researchers like myself have studied this. And we found that for whatever reason, the human brain will struggle with this idea of like being able to put positive x whatever you want. That's a struggle, but it tends to cement the concept much better than sticking to always up, always positive, whatever, right? And then that minus sign gets missed and everything's wrong. So I've taught you this way for a reason. Did I answer your question, Griffin? Okay. All right. I do a little check. I make sure, okay, I got 2 forces and there were 2 forces. It's very easy for me to like lose track of all my forces. Sometimes people put these in tables. I think Dr. Kerfoot teaches, like you make a table X and Y and you write down all your forces in the X and Y just to make sure you have them all down. And then you go and stick them into your, but like that, it's just different ways of doing the same thing, right? For me, I just visually check. I look and see, okay, I got 2, I've got 2, I've got the right directions on them, I'm good. Okay. What about the Y direction? Again, we're just sort of just looking here, right? So what have I got? Normal and how many times have I lost points on getting cosine and sine flipped? The answer is all of them. Normal, positive or negative? mg cos theta? Anybody confused on why the mg cos was negative and the normal was positive? It's okay to admit it. Admit it now. Don't wait till Thursday. Okay.
Why are we identifying, I know you already said it multiple times, but the mg sine theta as or never mind.
Got it? Good. Okay. I've already forgotten what we're solving for acceleration? Okay. My acceleration is sitting right here. In order to find it, I need to know the friction. Let's pretend I know m and g and the theta. Okay? So, what's the connection between friction and normal force? Insert bad dad joke here. Right? Because this is so much fun. So I can substitute that into there. After I've substituted that into there to get the following. I did skip about 4 algebra steps right there. Just so you know, right? I'm a professional driver on a closed course. Do not attempt. Right? Do all the algebra. This equation right here, because there was a 0 over here, turned into n equals mg cos theta. That got inserted, so this is mu mg cos theta. And then that gets put into there, which is mu mg cos theta, which is right there. And then I just carried along that for the ride. Okay, what's the same in every term? So my acceleration, mu g cosine theta plus g sine theta. That'll be, assuming I know mu or g or angles or whatever. Right? At this point, like, we solve for acceleration, but we could solve for mu as long as we knew the acceleration. Right? So, yeah, lots of different ways to do it. But that's the setup for Newton's second law. It is slightly different, though, from the one we got that we did together with somebody, was it sliding down the hill? We got a minus sign in our equation for that one. So you can think about why these are, yeah, let's think about that. Why are these both positive? We're taking this and adding it to this, making the acceleration bigger than if there was, like, say, a minus sign in there or something, right? Okay. Are these two forces working together to accelerate the object? Yeah. It's exactly what they're doing. That's what this says. Because it's added together, they're working together. When we did the problem last time with them sliding down the slope and the friction was up the slope, friction was fighting gravity. And so we got that negative sign in there.
And we can just determine that from the algebraic steps.
Yeah, let the algebra, work the algebra, and then stare at your solution for just a little bit and make sure it makes sense. And by make sense, I mean, like, look at the signs, right? If two forces are working together, they should have the same sign. If they're working opposite each other, they should have different signs. Like I know normal and mg cosine theta are opposites because look, one of them's negative, right? They're just working against each other.
After we finish and get our acceleration formula, what does our U represent?
It's the coefficient of friction. It's just like how slippery or frictiony the surface is. So like at the Olympics on the bobsled track, it's really small. It's like 0.001 or something like that. The ice is really, really tiny. Between your shoes and the floor, it's like 0.5. Tires in the road is like 0.4. So yeah, it's material dependent, surface dependent. Put water on the surface, it goes down to like 0.1, depending.
If we didn't know U, couldn't we still solve it?
Not really. Like you'd have to know mu, g, and the angle to be able to get the acceleration. So those would have to be given. Yeah. That's how we make up problems for homework and tests and stuff like that. Is you just throw down a problem and then at the end you decide, okay, well, are we asking him to look for? Let's ask him to look for mu, right? Because it's just the only thing that's different would be the algebra that you would do to solve for it, right? The physics is the same. Kind of why, annoyingly, physics teachers like me will say, well, there's really only one Newton's second law problem. And you're like, but no, Mr. Balogh, it comes out differently every time. Yeah, I know it comes out differently every time, but there's still only one Newton's second law problem. Draw a free body diagram, write down Newton's second law, get your directions right. That's the problem, right? Everything else is just sort of details, and usually mathematical ones that are not very interesting. Yeah? I'm not sure I understand your question.
Like how you substituted F equals
Yeah.
U n, and then you got the acceleration
Mm-hmm.
equation. I'm just like kind of confused how you like converted it into that.
Like algebraically?
Oh, doing the math?
Yeah.
You want to see the math? In green, here's the math. You're lucky, I'm not a math teacher. This could get really bad if I was a math teacher. Okay, and so those are the three equations I have, right? I want A. A is what I'm after, and I need to get rid of things that I can substitute away, right? So I'm going to start with the middle equation just because it's simple to solve. If I move the mg cosine theta over to the other side of the equal sign, what happens? It becomes positive cosine. Right? So that's what my normal force is. And then if I substitute this into here, this is F equals mu mg cosine theta, because normal is equal to mg cosine theta. So now I've got what F is. And then I'm going to take this F, and I'm going to put it right in here. So MA, and then I write what F is. It's mu mg cosine theta plus mg sine theta. Am I going too fast? I'll talk very slowly, like every math teacher would. Go back and replay this over and over again. You'll catch on. All math problems are strategy problems. Start with what you know. Know where you want to be. Like I started with this idea in mind. A equals something. That's what I was after. I don't know what the something looks like. And that will all come out in the wash as I do the algebra. But I know I want to get A equals something. I could have started right here, A equals something. I could have divided everything by M. But I didn't do that because I don't like fractions. It's totally possible to do it that way. It's just I decided I wanted to get F since I already knew what F was, and I can just kind of keep breaking it out. So it's a little bit like chess. You got to be thinking a couple steps ahead of where you want to get. And what I wanted to get was no F, no N. And I knew that I didn't want F and N because I had equations for them. Like I was being told what these were. And so that means I can substitute into different places to get rid of that symbol. I wanted the least number of symbols I could get in my answer. That's typically what you're after in mathematics. The more things you can eliminate, that's something less that you have to go figure out or measure or define. And we're just getting down to the simplest set of conditions. And then once I'm finally here, I cancel all my m's out, and then I get what's in the black box. Maybe I should pretend to struggle more with my math so you guys feel better. But this isn't a math class, and I don't like wasting time on math because math can get figured out. The tutors in the tutorial center can help you with math, right? But unless you find a physics tutor, the math tutor is not going to be able to help you with the physics, which is what this class is about and what I look at. You guys know this, right? Annoyingly, what do I grade you on? The setup, right? If you make a math mistake, I might not catch it, number one. And number two, if it's a simple math error, I might be like, don't care, not a math teacher. Full credit for physics. What kind of thing would I give you a -2 for? Getting these wrong. That's an automatic -2. Why is that an automatic -2? That's not, you're not doing physics. At best, you're guessing. Okay? Obviously, legitimate mistakes happen where you drew the free body diagram and then like one of the signs over here got wrong, right? Okay, so if I see a wrong sign, I'll look at your free body diagram. If your free body diagram's right and you just got the sign wrong, that's probably -1. But this is these are key physics things right here, right? Missing, if you didn't have this listed, that's a key physics thing. That's a fundamental flaw in the setting up of the physics. If you've got, I'll be honest with you, usually if you've got this and a free body diagram that's correct, I'm like, that's a 2. I don't care what the answer is. Because what's the rest of the answer? It's math. And I'm less concerned about that. I know technically in the syllabus it says it has to be a correct answer and all the physics needs to be there. But come on, in a testing situation, for you to get this, that's worth a good job, right? Right? That should be celebrated. After that, whatever. And like I said, I do tricks, right? I might, to make this easier, you set this all up, I'll just give you what the frictional force is. Right? If I just give you this number and you have all these numbers, can you find A? Yeah, and then you don't have to do any of this substitution stuff. I can't remember if I did it on this exam, but I have a tendency to do stuff like that, right? When you've got a difficult problem to solve. So make the math easy. Physics is hard enough. Did I answer your question? Okay. If you're still stuck, we can talk about it. So tomorrow, what's happening tomorrow? We got a lab, right? I'm going to level with you. Should probably not record this kind of things. Tomorrow's lab has dubious value in helping you understand centripetal acceleration. Why don't you come and get help on finishing up your homework? That's due tomorrow, right? Finishing up your homework and going through math and getting extra problems to try to do. How does that sound? Let's do that instead. Let's call an audible. Okay? Tomorrow's lab will not be the lab. You're not missing out on much. Okay? Let's do whatever it is you guys want to do. So it's going to be more like grasp. You're going to come in, you're going to have to ask me, Mr. Balogh, I want help with this. Or I want a sample problem. Can you give me a sample problem for static equilibrium, right? And work on it and get help. Does that make sense? So you've got me for 2 hours, 50 minutes in whatever lab section you're in to just get whatever help you need to be ready for the test on Thursday. How's that sound? Let's do that. Okay? We'll do that tomorrow. All right, so that was Newton's laws. Static equilibrium? We'll go over that? Okay. Didn't you have wasn't there a homework problem? Oops. Was it a climber? Like some person was hanging by a rope. Oh yeah. Not that problem, Mr. Balogh. I require counseling now. All right. I don't remember which angle you were given. But were they like given up here?
Yeah, it was at the top.
Because that's harder, so why not do that? I'm going to redraw this just slightly.
It was at the bottom.
It was at the bottom? I don't care. It doesn't matter. It's just an angle. I know it matters the world to you guys, but it actually doesn't matter. I'm exaggerating here. And the box is our climber. This could be UPS delivering something in the Himalayas. I don't know what this is. Okay? But it's something dangling like that, right? And let's say that we are given this angle, we'll call it theta 1. And we're given this angle right here, we'll call it theta 2. And we're given the mass of the package. And we're told that there are tensions in these two ropes. Find the tensions. It's usually like in equilibrium problems, that's usually what's going on. Okay. So it was something like this, I'm pretty sure, right? Yeah, okay. So a static equilibrium problem is a Newton's second law problem with a very special acceleration. What's the acceleration? 0. So our template, instead of being ma equals, is what? 0 equals. Zeros are fun because they make things easier, right? Okay. You're like, this isn't easy, Mr. Balogh. You're right, this is a little bit harder, I think, because we actually have to go find components for both of the tensions. Why do we have to do that? Well, there's no real way to put a coordinate system where 2 out of 3 of these forces are lined up on the coordinate system. Like I can't, if I rotated the coordinate system to be on this one, then I'd have to find components of this force and this force. If I lined it up with this one, then this one's not aligned and this one's not aligned. So there's really like no way to scoot around the fact that we're going to be finding components of things, multiple things. And so we might as well stick with a straight uppy down, lefty righty coordinate system. So that's what we're going to do. With the acceleration being 0, we've kind of robbed you of that, oh, just put it in the same direction as the acceleration. We have no acceleration, so you're free to pick what you want. I'm going to choose straight up and down and straight left and right. So in doing that, right, I now have some problems. What two forces do I need to find components of? The tensions, right? I have mg, and then I've got those two tensions that I've already drawn out here, right? Tension 1 acting up like this. I'll put it in red. Tension 2 acting up like that. Okay. We need to find the pieces of each of these. Okay. So what direction are the components for T1? Which way does T1 point? Up and to the... So that's the answer for your components. If T1 points up and to the left, your two components have to point which way? Up and left. So I'm going to draw up, oops, and left, right? Those are the parts of T1. Okay, which way does T2 point? Up and right. So what are the components going to be? Up and right. I didn't make them long enough, but you get the idea, right? Okay. All right. So let's do the purple ones first. The one pointing to the left, the horizontal component, sine or cosine? Why is it cosine? It's touching theta 1. And what about the vertical one? Is it touching theta 1? No. So T1 sine theta. All right, for the blue ones, x component, is it touching angle theta 2? Here's theta 2. Here's the angle. Is it touching? Yep. So? Good. Theta 2. And then this one will be T2 sine theta 2. So we had to go find components of two things. What's the next step? Hint, it's exactly the same as what we did over here. Once we have our free body diagram, what do? We translate that into our template, right? Our free body diagram informs us of what we're going to put over here. So if we look at the template and we're looking at x, we only look along this line, the x direction. What do I write? I write down the forces that are along the x direction. And then I go back and get their signs. What's the sign on the first one? It's the same process. Different equations, different symbols, different situation, same exact approach. All right, now I do the vertical. What have I got here? Some of you are like, oh, we should be able to put the two t's next to each other. No. They're all in the y direction. What matters is what I do next. T1 sine theta 1, positive or negative? Mg. T2. What happens next? Algebra. Algebra what happens next, right? So you got to solve for both T1 and T2. I got two equations with two unknowns. This is a horror show. Because I've got to, I'm not going to do it, but I've got to solve, maybe solve this equation for T2. And once I got T2, I plug it into here. And then I'll have T1s that I have to like factor out and all kinds of stuff. It's nasty. But it's just math. I mean, I took math a long time ago. I don't want to do it. What?
Did we determine that the y was positive and x was positive from that way just because of the
I didn't have an acceleration to inform me of what to do. So I just decided, go standard. Rotating it here would just be, it would be doable, but it would be extra hard to find all the angles. We were already given angles referenced from a horizontal and vertical, so just use that as your reference frame. One thing that does throw people sometimes in static equilibrium, the thing you're drawing a free body diagram of may not be like truly physical. Like, do you notice how we didn't draw it of the climber? Like, the climber's free body diagram is just that, isn't it? The rope they're hanging off of and gravity, which doesn't really help, right? So what we did is we drew a free body diagram of where all the ropes meet. Sometimes that throws people. You can do that. Where all the ropes meet, draw the free body diagram there. All right, fine, I'll do the math. You didn't ask for it, but you're going to get it anyway. T1 cosine theta 1 equals T2 cosine theta 2. What did I do right there? I moved the T1 cosine theta 1 to the other side, which makes it positive. A lot of you are saying, add T1 cosine theta 1 to both sides. Yes, those are identical things. They're equivalent. Okay. Then I'm going to divide by cosine theta 2. So that T2 is equal to T1 cosine theta 1 over cosine theta 2. What did I do that for? Because I want to put that right there. So that this equation becomes T1 sine theta 1 minus mg plus, and now I substitute in, which is T1 cosine theta 1 over cosine theta 2 times sine theta 2. And because I'm a clever boy, a sine over a cosine of the same angle is a, and I don't like fractions. Okay. So now I have T1 here and a T1 here. So I'm going to factor those out. T1, what do I leave behind? A sine theta 1 plus a cosine theta 1 tangent theta 2. So this was attached to this T1, and this T1 right here had a cosine and a tangent. Those are the leftovers. They end up in parentheses. And then I can't forget my minus mg, right? This is equal to 0. So to solve for T1, move the mg over. If I move the mg over, it becomes positive, doesn't it? And then I'm got equals the rest of this stuff. And how do I get T1 by itself? Divide by the thing that's attached to it. Oh boy. Sine theta 1 plus cosine theta 1 tangent theta 2. And this will be equal to T1. And because I did it with electrons, I can kind of fix my mess. Nope. Whatever those things are, that's the tension in rope number 1. So how do I now find the tension in rope number 2? Put that back up in there because I've already solved for what tension in rope number 2 is. Yep, I'm just checking it. That tension, yep, because mg is going to pull it down, increasing the tension. I'm just checking all my signs. The angles will add to that. Yeah, no, this I'm happy with this because I get worried if I had some minus signs in it somewhere because those tensions are being affected by the mass and the angles and all that kind of stuff, right? This gets much easier if that guy were hanging or gal were hanging in the middle. If the person was in the middle of the rope, then what's true? The angles are the same, which means the tensions are equal, right? And so that does make the math a whole bunch easier. Yeah, I will in a second. Okay. How has this helped you? How has this hurt you? Well, how? Like, what has it done for you? We did this at the very beginning of the unit, didn't we? Okay, the conservation of energy stuff's kind of fresher in our brains because that's the homework you're working on and stuff like that, right? So it's very natural to sort of focus on that because it's fresh and all that sort of stuff. But going back and refreshing this is good. That's okay, good. Any other ways this maybe has helped you? The whole process we've done today. What has been good about it? The practice, clarifying, seeing it again, really.
Figuring out why certain things happen for what reason.
Reinforcing that, because I called that out the first time we did it, but again, how has this hurt you? Is there something that's not helped you today? I'm looking for feedback, things that you can help me be a better teacher. Yeah.
So for the TF part, so how can you tell which is sine and which is cosine?
When I was doing the purple and the blue,
Yeah.
I was doing trig. I did touching, not touching, but you can do SOHCAHTOA if you want. Which one are you more comfortable with? SOHCAHTOA. So I'm looking at a triangle. So I've got this side right here, and I've got a hypotenuse. Really, what's going on? I'll do it in purple over here. Okay, there's a triangle that consists of T1. This side T1x, and then I drew the component, but I didn't, like, these form a right triangle right there. And then there's that angle sitting right in there. So if we did SOHCAHTOA and we wanted to find this side, that side, is it the adjacent or opposite side? Adjacent, so cosine, right? I just, instead of having to draw the triangle and do SOHCAHTOA, I just look at my component and I see that my angle is drawn. See that line that indicates the angle? It touches the hypotenuse and this side, so I know it's got to be cosine.
How did you get the tan?
That was a mathematical artifact right here. Sine over cosine of the same angle is tangent. I just didn't want to have to write a fraction, because fractions since third grade have always scared me. Did not have a good day with fractions. Never have. Never will. They're not welcome in my home. But I mean, did anything like hurt you or waste your time, or like what? If I keep doing what I'm doing, I'll be all right. Will you guys be okay?
All of this has been incredibly valuable.
Okay. It's just sometimes, right? I got to check because you guys learn differently now than the way I did, right? I've been having discussions. Some people have been emailing me. AI, especially ChatGPT, seems to be kind of going off the rails a little bit with the conservation of energy problems. It keeps trying to do Newton's laws instead of doing conservation of energy. So that's another interesting. We can maybe talk about that a little bit tomorrow. You can, if you guys are using it, show me what it's doing, because if it's confusing you, right, you need to figure out how to prompt it correctly.
I used 3 different AI softwares to understand a problem because I got an answer and the AI supported my answer for all of them, but then the homework kept saying
Kept saying
I was
it was wrong. Did it turn out the homework was wrong, or was?
that I'm not sure.
Let's look at it tomorrow.
I don't know.
Let's look at it tomorrow. It's a really good time to troubleshoot. Would be tomorrow. Yeah, so that just means that it very well Wiley plus could be an error, right? This strategy of trying multiple AIs really helps, because if an AI does it differently than another one does, right? How do you do this without having to spend money? Did you spend any money to access 3 AIs?
You get a limitation.
Yeah.
But
Almost all of them will limit you to like a certain number of, it's not quite questions, but it's kind of like that, per 4-hour or 6-hour block. So if you hit the limit, you hit the limit, fine. But like, don't worry about, you don't have to pay to be able to try it. Right, the private browsing sometimes destroys the cookie and lets you keep repeating. But you can't like go back to the same thing you were doing. It has no memory of what you're doing. But yeah, there's different ways to get around it. I am heavily investigating Claude right now. I'm really putting it through its paces. It seems to be doing a pretty good job on the physics. Perplexity, that one's, I haven't tried that one yet. Yeah, right, Perplexity puts them all together. Right, right. So, yeah, but I mean, we can talk a little bit more about that tomorrow. We've got, I don't know, 10 minutes left. You guys want to stop and we'll just pick it up tomorrow? You can ask your questions. It's totally up to you.
I wanted to ask to go over the conservation of energy.
You want to? Oh, we didn't do conservation of energy, right? Let's do that. Let's do that. Sorry, guys. Some of you were like, I'm free. No. Well, you can go if you want. You're never forced to stay. Let's see. I've got super glue if I need to force you to stay. Conservation of energy. Can I do this one? I can do this one at the top of my head. I just wanted to make sure I did, yeah, the way that your book does it. Okay. Okay. And what does E naught mean? The initial, right? Final minus initial. I usually use F and I. That's how it stuck in my brain, how I was taught. Okay, so every conservation of energy problem more or less starts right here. Again, process, a template. What do, right? You start here and then you break down the different parts that a problem might consist of, okay? So let's see. We could do the bobsledder again. Okay? We could do the bobsledder again. Same bobsledder we had back here. But now, instead of finding either the acceleration, let's find the velocity at the top of the hill. Right? If we know the velocity going in at the bottom of the hill, let's find the velocity at the top of the hill. That's what we're going to do. So here's our hill. Here's our bobsledder, right? They start with some sort of initial velocity. They end with some kind of final velocity. What three things do we have to be able to do anything with conservation of energy? Three definitions. Initial, final, zero. You've got to label that, because if you don't, you're just, at best, you're throwing spaghetti on the wall to see what sticks. So, initial, final. How did I know to put initial and final there? It was where it starts and where it ends, right? Like we know how fast it's going at the bottom. We're trying to find how fast it's going at the top. Where do we put zero? Lowest point in the problem. Okay? All right, so with those three definitions in place, I can now start asking questions. Like, is there any work in this problem? Is there a force besides gravity that's doing work in this problem? We have to do a quick free body diagram just to make sure that we haven't forgotten anything. But luckily enough, we already did one. Right? Okay. So the quick free body diagram is normal, gravity, and friction, right? The distance that this bobsled is traveling up the slope gives us a clue about the work done by the normal force. Does normal force do any work here? No, why not? It's perpendicular, right? It's not parallel to the surface. Okay, so there's no work done by the normal force. Is there work done by gravity? Yes, but we don't put it in the work non-conservative. It's going to end up in the potential energy due to gravity, right? So the only force we have left over that can do any work is the work due to the friction. So that's what our work non-conservative is. Gravity is handled in the energy terms. We have gravitational potential energy, so we're going to do it there, not work non-conservative. Work non-conservative is for anything that's not gravity. If it's gravity, it doesn't go work, and non-conserved goes on the other side. Okay, final energy. What is it doing at the final point? Is it moving? Yeah. So it has 1/2 mv final squared, right? What kind of energy is that? Kinetic. Does it have potential energy up there? Yeah. Okay. Minus, same questions, but at the bottom. Is it moving at the bottom of the hill, the initial point? Yeah. Does it have gravitational potential energy down there? No. Why not? The height is equal to 0. We put 0 there, right? Yeah. This is kinetic energy final plus potential energy final minus kinetic energy initial plus potential energy initial. Does that help? Not so, I mean, okay, hold on a second. I love electrons. There we go. Okay. So you can start with K final plus P final minus the sum of the initials, right? And then write down the equations. It's a perfectly valid way to do it. All right, what are we going to do about work final? What is work? Oops. Work is force times distance times cosine of the angle between them. The distance is up the slope and the friction is down the slope. So that gives us a hint. It's negative, right? So it's minus F times D. Where'd my cosine theta go? It is the negative. Because what's the angle between the direction and the force? 180. What's cosine of 180? Negative 1. Right? So this is force times distance times cosine 180. Cosine 180 is a negative 1, right? So it becomes minus FD. I tend to not think about this. I just go, oh, force opposite D, negative FD. Okay, and then we got all this garbage over here. Garbage. All this physics over here. Okay, so, and then we math out this for the final velocity. But there's still one thing we kind of don't know, and that's what the frictional force is. If they gave us the frictional force, that would have been nice, right? But they didn't. So you do have to substitute in this. But in order to do that, you have to know what the normal force is. And do you remember what the normal force was over here? Yeah, it's mg cosine theta, right? So a little bit of recycling from Newton's second law. But that F can now get inserted into there. And then you solve for VF, whatever that turns out to be. Looks like there's an M in every term. So that's probably going to cancel out. And with 1 minute left, I'm not going to torture you through. I was saved by the bell. I don't have to do any more algebra. Okay, so throwing an audible for tomorrow. Come in, get help. Right? Come in, get help. We won't do the lab. It'll be set up in there because, well, maybe I'll go tell the lab person to not bother, but see you tomorrow.